Assalamu alaikum. Welcome to this MATLAB tutorial. In this tutorial, I am going to teach you how to design automatic generation control of two-area power system using MATLAB Simulink software. For this purpose, I have taken an example from the book Power System Analysis by Hadi Sadat, Chapter 12, Example 12.4. Consider the example, which consists of a two-area power system connected by a tie line having the following parameters on a 1000 MVA common base. Both power plants are operating in parallel at the nominal frequency of 60 Hz. All of a sudden, a load change of 187.5 MW occurs in area 1. Due to this, system frequency will vary as well as the power plants have to enhance their generation in order to meet the increased load demand. In this situation, we have to determine the new steady-state frequency and the change in the tie line power flow. For this purpose, we have to design this model in the MATLAB Simulink software. The mathematical solution as well as the basic model of this example can be found in the Hadi Sadat book. I am going to model it again in order to explain various other results which can be obtained from this model. For your convenience, I have uploaded the PDF link in the description section. You can download it from there. To design the model of two-area power system using transfer functions, first just look at the block diagram of single-area power plant based on transfer functions. It may be noticed that model consists of transfer functions of governor, turbine, generator named as rotating mass and load. In the feedback, speed regulation is placed. It means that to model the power plant we need transfer function block, gain block, sum block and input signal block. Now look at the block diagram of two-area power system using transfer function. It may be noticed that if single area power plant is successfully modeled in MATLAB Simulink software, then two-area power system can be easily modeled just by repeating the same procedure of single area power system with only addition of tie line power flow known as delta P12. Let's start. Just click on the Simulink icon to open it. Click on this icon to open a new model. First we need to save it. You may save it with any name of your choice and in any folder. To get the transfer function block, go to Simulink library and go to continuous. You can see here transfer function block is available. Take this block and bring it in the model. Look at the figure. We have to connect the rotating mass and load transfer function block. It may be noted that the inertia constant of area 1 is given as 5 seconds and d1 is equal to 0.6 as given in the example data. Furthermore, inertia constant is multiplied by 2, therefore it becomes 10. The total inertia and the load transfer function becomes 1 upon 10 as plus 0.6. Therefore, double click on the transfer function block and write here 10, 0.6 and press OK. Write here inertia and load 1 to represent the area 1. Now look at the figure again. We need a summer block. Take the add block from here and bring it in the model and connect it with the inertia and load 1. Look at the figure again. Now we need turbine transfer function. For this purpose, just copy this transfer function block and paste it here. Connect it with sum block. Write here turbine 1 to represent the turbine of area 1. The time constant for the turbine of area 1 is 0.5 as given in the example data. Therefore, double click on the transfer function block, write here 0.5 and press OK. Look at the figure again. Now we need governor transfer function. For this purpose, just copy this transfer function block and paste it here. Connect it with the turbine block. Write here governor 1 to represent the governor of area 1. The time constant for the governor of area 1 is 0.2 as given in the example data. Therefore, double click on the transfer function block, write here 0.2 and press OK. Look at the figure again. Now we need sum block. For this purpose, just copy this add block and paste it here. Connect it with the governor block, double click on it, put negative sign and press OK. Look at the figure again. We have to put speed regulation block in the feedback loop. For this purpose we need gain block. Take the gain block from here and bring it in the model. Connect this gain block with inertia and load block. Connect it with the aid block in order to complete the feedback loop. Write here 1 upon R1 to represent the speed regulation of area 1. Speed regulation given in the example for area 1 is 0.05 per unit. Therefore 1 upon R1 for area 1 will become 20. Double click on the gain block, put here 20 and press OK. At this stage power system of area 1 is almost completed. Now we have to design the model of two area power system. Just look at the block diagram of two area power system. It may be noted that two area power system basically consists of the two models of the single area system. Therefore to design the model of two area power system, just copy the whole model and paste it here. Now it shows two area power system. Only change we need is to put the parameter values of area 2 in the different blocks. It may be noted that the inertia constant of area 2 is given as 4 seconds and d2 is equal to 0.9 as given in the example data. Furthermore, this inertia constant is multiplied by 2, therefore it becomes 8. The total inertia and load transfer function for area 2 becomes 1 upon 8s plus 0.9. Therefore, double click on the transfer function block and write here 8, 0.9 and press OK. Now the time constant for the turbine of area 2 is 0.6 as given in the example data. Therefore, double click on the transfer function block, write here 0.6 and press OK. The time constant for the governor of area 2 is 0.3 as given in the example data. Therefore, double click on the transfer function block, write here 0.3 and press OK. The speed regulation given in the example for area 2 is 0.0625 per unit. Therefore, 1 upon R2 for area 2 will become 16. Double click on the gain block, put here 16 and press OK. Look at the block diagram of two area power system. It may be noted that now we have to add blocks to include the tie line power flow, which is given by delta P12 is equal to PS into the difference of the frequencies between the two generators. Here delta sigma 1 and 2 basically represents the change in angle of the generator 1 and 2. This change in angle occurred due to change in frequency. Therefore, to model it in the Simulink, we need a summer block and add the change in frequency signals with it. For this purpose, copy the add block and paste it here. Double click on it, put here one positive sign, one negative sign and press OK. Connect the positive sign with area 1 and connect the negative sign with area 2. Look at the figure again. Now we need to put an integrator and a gain for synchronizing power coefficient known as PS. For this purpose, take the integrator from here and bring it in the model. Now copy the gain block and paste it here and connect it with the integrator. Write here PS to represent the synchronizing power coefficient. The value for synchronizing power coefficient is 2 as given in the example data. Therefore, double click on the gain block, put here 2 and press OK. Look at the figure again. Now we have to connect both areas through tie line. Therefore, double click on this add block and put here one negative sign, one positive and one negative sign and press OK. Now connect this negative sign with the gain block. Similarly, connect it with the positive sign of this add block. Now we need the input signal, which consists of change in the load demand. For this purpose, we need step input signal. Take the step input signal from here and bring it in the model. Connect it with the sum block. Double click on it. A window will open. Write step time to 100. Just look at the example data, which shows that for a 187.5 megawatt change in the load, delta PL1 is 0.1875 per unit. Therefore, put here 0.1875 as initial value as well as final value and press OK. Now we need to connect the scope for different measurements. For this purpose, take the scope from here and bring it in the model. Connect it here and write dp12 in per unit. which represents the delta P12 and measures the change in tie line power flow. Now copy this scope again and paste it here. Connect it here to measure the change in frequency in per unit for area 1. Write here dF1 in per unit. Similarly, copy the scope and paste it here. Connect it here to measure the change in frequency in per unit for area 2. Write here dF2 in per unit. Now copy the scope again, paste it here and connect it with governor output to measure the change in mechanical power for area 1. Write here PM1 in per unit. Similarly, copy the scope, paste it here and connect it with output of governor 2 to measure the change in mechanical power for area 2. Write here PM2 in per unit. Set the simulation time to 50 seconds. Now you can run the simulation. Double click on the scope to see the frequency deviation response in per unit of area 1. Compare the result with the result in the example. You can see both results are correct. Now double click on the scope to see the frequency deviation response in per unit of area 2. You can see that frequency response of both areas are same. Now double click on the scope to see the change in mechanical power in per unit for area 1. Compare the result with the result in example. You can see both results are correct. Now double click on the scope to see the change in mechanical power in per unit for area 2. Compare the result with the result in the example. You can see both results are correct. Now to get the clear idea, we want to change this frequency deviation in per unit of area 1 into Hertz. We know that change in frequency in Hertz is equal to change in frequency in per units into base frequency. The base frequency is 60 Hz, therefore multiply the result with the gain in order to get the frequency deviation in Hz. To do this, copy the gain block, paste it here, connect it and write here base frequency. Double click on it, put here 60 and press OK. Now connect the scope to measure the frequency deviation in Hz for area 1. Write here dF1 in Hz. Similarly, copy this base frequency, paste it here to measure the change in frequency in Hz for area 2. Copy the scope, paste it here and connect it with the base frequency. Write here dF2 in Hz. Now you can run the simulation. Double click on this scope to see the frequency deviation in Hz for both areas. Compare the answer with the answer obtained in the example. You can see both answers are correct. This is the frequency change in both areas when a load of 187.5 MW is suddenly added to the system. Now what will be the original frequency of the system? The steady state frequency in Hertz is given by F actual is equal to F original plus change in the frequency in Hertz. To do this, we need again sum block. Copy this sum block, paste it here and connect it with this point. To add 60 Hz frequency, we need constant block. Take this block from here and connect it here. Double click on it, write here 60 and press OK. Copy the scope and connect it here. Write here actual frequency F1 of area 1 in Hz. Repeat the same procedure to measure the frequency in Hz for area 2. Now run the simulation again. Double click on the scope. It shows the area 1 original frequency when 187.5 MW of the load is added. When load is increased, the system frequency is decreased. Therefore, in this case, frequency decreases to 59.7 Hz. You can compare the answer with the answer obtained in the example. You can see both results are correct. Now we want to see the power graphs. First, we are going to see the delta P12 change in tie line power flow. It shows that tie line power which flows from area 1 to area 2 is 0.0845 per unit. You can compare the answer with the answer obtained in the example. You can see both results are correct. Now to get clear idea, we want to change this tie line power, mechanical power in area 1 and 2 in megawatt. We know that the actual change in load power is equal to per unit change multiply with the base load power. The base load power is 1000 MVA. To do this, copy the gain block and paste it here. Similarly, copy the scope and connect it with gain block. Write here dPm1 in megawatt to represent the change in mechanical power in megawatt for area 1. Double click on the gain block, write here 1000 MVA and press OK. Write here base MVA. Now run the simulation, double click on the scope. It shows that for a 187.5 megawatt of load change in area 1, 100 megawatt of power is enhanced in area 1 to meet this increased load demand. You can compare the answer with the answer obtained in the example. You can see both results are correct. Now repeat the same procedure for area 2 to measure the change in mechanical power in megawatt. Now run the simulation. Double click on the scope. It shows that for a 187.5 megawatt of load change in area 1, 80 megawatt of power is enhanced in area 2 to meet this increased load demand. You can compare the answer with the answer obtained in the example. You can see both results are correct. Now repeat the same procedure for change in tie line power flow from area 1 to area 2 in megawatt. Now run the simulation. Double click on the scope. It shows that for a 187.5 megawatt of the load change in area 1, 84.5 megawatt of power flows through tie line from area 2 to area 1. You can compare the answer with the answer obtained in the example. You can see both results are correct. Now I am going to discuss the most critical points about this model and its results. It may be noted that the load of 187.5 megawatt is changed in area 1 power system only. However, from the results it has been observed that both generators have enhanced their generation to meet the increased load demand. Practically this is not true. In the real practice, if sudden load is changed in any area, then each area has to absorb its own changes, or in other words, it has to be supplied by the generators of that area only. It means that for a load change of 187.5 megawatt, the change in mechanical power of area 1 should be increased to 187.5 megawatt only, whereas the change in mechanical power of area 2 must remain 0. Furthermore, change in tie line power should also remain 0. To do this, we need to do some changes in the model in such a way that change of the load in any area may cause the change of generation in that area only. Furthermore, it may be noted that frequency of the system has reached up to 59.7 Hz. It has not recovered to 60 Hz, due to which, despite of 187.5 megawatt change in the load, only 180 megawatt of load has been supplied by both the generators. It still lacks 7.5 megawatt. When frequency will recover to 60 Hz, both generators will be able to supply the whole 187.5 megawatt. It means that we need to use some controlling techniques in order to bring the frequency to its nominal value of 60 Hz. Moreover, it may be noted that change in mechanical power of generator 2 is 80 megawatt. It means that 80 megawatt of power is supplied from area 2 to area 1 through tie line. However, the simulation results have shown that the tie line power flow is 84.5 megawatt. Now question may arise that how it is possible. The answer to this question is that 80 megawatt is supplied from area 2, whereas 4.5 megawatt of power is reduced in area 2 due to the frequency drop. It is because frequency stays at 59.7 Hz. This reduction in frequency causes the reduction in load, due to which this additional power of 4.5 megawatt also flows towards area 1. Therefore, overall 84.5 megawatt of power flows from the tie line. Friends, due to the limitation of the time, I will discuss the solutions of all these points in the second part of this video. Therefore, in second part, I will discuss the following main points. Number 1. What changes will be done in the model in order that whole 187.5 megawatt of load change in area 1 should be supplied by the generator of area 1 only. Number 2. What changes are required so that both areas supply their power when change in the load occurs in both areas. Number 3. How to use this model for bachelor, master or one objective of PhD research. Number 4. What other research ideas can be added in this model to extend this research. That's all for today's tutorial. I hope you really enjoyed this tutorial. Friends, I upload many videos based on various topics of power system and motivation on regular basis. Therefore, don't forget to subscribe my channel in order not to miss my latest videos. And don't forget to share my videos with your friends and class fellows so that they can also get benefit from these videos. Thank you very much.